So I've been having a chat with someone in the messaging on one of my videos who was interested in one of my schematics. Anyway, I directed him to a slightly revised version of it, and he'd tried simulating it and had some issues. I can't remember your name, mate. I'm hoping you watch this video. Anyway, so having a look at the schematic, and it dawned on me there are actually a few mistakes in it. So the reason being, Symmetrics, which is the simulator I drew this in, the free version you're limited by the amount of circuit nodes you can have, and because the amount of op amps in here, it exceeds what you can simulate in one go. So when I originally designed the circuit, I'd done it in chunks, and so when it comes to printing it out for this one, I literally just copied and pasted it between the schematics. Because it was done on different sheets, it didn't really fit together, so I've stitched it together, and I've made a few mistakes along the way. Sorry about the creaking. This chair is a very creaky chair. So in the original schematic, first of all, the loss of AC circuit, you can see, look, I've got 47k here on the input resistor rather than 1k. I've got 100k as the discharge resistor rather than 10k, and I've got a Zener diode there to clamp the voltage at 8.2 volts. So it's on the assumption that it's running off 12 volt AC. So I will say the whole circuit, for this circuit to work reliably, it would need a DC power supply. You'd normally have a 12 volt dual secondary transformer. So you'd rectify that, get about plus minus 18 volts, and then it would need to be fed by two 12 volt regulators, and they need to be solid 12 volts because it uses various voltage references derived from that supply. So anyway, as I've been redrawing this, I've took out some unnecessary components. So for instance, various capacitors here and here, and yeah, that one, they're not needed. It's running off a stable DC supply. I don't really know why they're even in there. I've put some 1k resistors in, so you can see every single op amp, there's no direct feed to any connection to any of the inputs. It always has to go for a minimum of 1k resistance. That's quite handy. Say there's an issue with your power supply and one of the rail collapses or something, or there's a random transient spike finds its way through somewhere, or something latches up through some weird set of circumstances, it will help protect the op amps. It stops them having a direct current path to somewhere. It limits the amount of current that can pass through that input. Should never happen. It's also good for like static discharge and stuff. It also helps with like RF noise and stuff. It's handy. It's always good practice. It can, even if it's just to help build the circuit board, because sometimes having that 1k resistor gives you a track to go under also. That's been added. What else has been changed? So, a big change I went through, rather than having there's some odd values in here. Look, 180 nanofarads, 2k7, 18k. They're just weird values. They're not your sort of common values you find in your parts bin. Whereas, so 22ks and 10ks, everyone has reels of them if they do anything with electronics. Same as 100k, 220k. 47k. So most of the parts now are sort of 10ks and stuff. They're 22k, 10k. The capacitors 220 nanofarads. Everything's been changed for more common values, and some major issues with this. This is where it come to head. So other things I noticed. So look, 220 nanofarad here after this 10k. This just adds some high frequency filtering, stops it going through the rest of the circuit. For some reason here, I've cut it coming up, going back down. It goes straight to the 100 nanofarad. That will probably cause this to oscillate, to be honest, because it's trying to drive a 100 nanofarad load. It's doing nothing, and then there's some 1ks into here. So that's how it should have looked. 1ks joining together to the 220 nanofarad, and then a buffer resistor on the output of this stops these swinging up and down as the frequencies go up. They only really respond to lower frequencies. But yeah, this 555 circuit. So first of all, it would have never on a 555, when this pulls low, the output goes high, which was what turns this transistor off. So this transistor, when it's conducting, it's what's closing the relay coils and allowing the speakers to connect. With this being low all the time, this would always be high and this transistor would never turn on. So there should be a diode across this resistor reverse bias. So this needs to be a much bigger capacitor. So when the circuit first powers up, this output cannot go low until this capacitor charges above 1/3 supply voltage. So the supply will quickly jump up to 12 volts. This capacitor slowly charges over the course of about 1.5 seconds or so to 4 volts or so, and then the output will go low, turning this transistor on. So there should be a diode there doing that. This diode is the wrong way round. It should be like this, with the cathode facing towards the capacitor. And so that's just purely when either of these detectors swings low, it stops the trigger pin being pulled any more than about 0.6 volts below the ground terminal on the 555. It's to stop spurious operation of 555 or stop it breaking, you know, stop any weird electrical fault happening. So yeah, and also this one, it would have ended up with some real weird behavior if there had been, say, a low frequency or rather quick succession of pulses being caught by the detector sent to the 555. It would have sort of triggered on and off rapidly, and then it could have gone into a latch state where it had gone through its trigger timing and was trying to time this up again and wouldn't have actually reset. Yeah, they don't like the voltages swinging around rapidly between them before things are stabilized. So this circuit is the correct one now. So the AC detector, it doesn't take long at all, a couple of cycles. I've put some more gain on the DC detectors. You can see I've now just drawn this for a stereo amplifier. So there's now a gain of 2. So somewhere around the 60 millivolt range or so is when it's got enough to trip either of these detectors. Like I said, more standard values on these parts. It has a few milliseconds. It's nothing major, realistic. Again, look, because I up those capacitors, I could actually lower this resistor to a more common part, so 2K2. It sort of pretty much evens out the timing anyway. And yeah, fix the issues with the 555. So this circuit is the correct one, which so in my last video I'm going on about some boards I had made for this. I wasn't really happy with them being super skinny, so I went back and I actually designed just a through hole component one, and I need to check this board. I've never actually got around to building it. You know, as happens, you know, the amplifiers that were meant to go along with them haven't got around to being built yet either. You know, just stuff happens and it gets in the way. I've been doing other bits and bobs. So I don't know whether these boards are any good. If the connection mistakes around here were made, some of the wrong component values don't matter because I can just change them as I'm soldering the board up. But I might, if I'm lucky, I might be able to just cut a few tracks and sort out the wiring mistakes that were made. As if I'd followed it off this schematic. I might have made the board, it's been that long now, I can't remember. I might have made the board actually going off the original schematics, but I doubt it. I'm going to say I probably actually made it off of this one. So, well, off of this one. So yeah, anyway, yeah, this video is more for old matey who's just been shown some interest in the schematic and the design, and he's just trying to simulate and stuff and see how it works. So yeah, this, if you want to play around, mate, this, I'm not guaranteeing it, but this should be a fully functioning schematic now. As far as I can tell, there's certainly no glaring faults like there is on the other one. I don't know how I missed, and there's more than a couple on this one. I don't know how I missed so many. It's one of those, you spend ages and ages on something and you can just get lost so many little bits and bobs. It's just what's staring you in the face. Basically, you can't see the wood for the trees. So, yeah. Anyway, this is the one, and just curious here. I've actually got my old Hawaii phone, which I've just strapped to my tripod, and I'm filming it with this because as much as I like that Ever camera I use, the audio on it is terrible. It has issues with you can hear the focus always hunting when it's fully zoomed out for some reason. I don't know why that is, but anyway, that's completely irrelevant. So, yeah, this is the schematic to go from if you're interested in my DC protection circuit. And as always, thanks for watching and catch you again.